For decades, hunters, hikers, and small-town sheriffs have watched the woods and noticed a pattern few have dared to name aloud. An inexplicable spike in Bigfoot sightings that doesn't come every year or even every decade, but on a precise schedule every 17 years. Reports flood in from different regions, different witnesses, different decades, but the timing is the same. What if this isn't coincidence? What if a hidden rhythm in the wilderness is pushing Sasquatch into the open on a predictable timetable? Picture an isolated forest town where the people know the season by sound, the steady hum of insects, the creak of old pines, the distant echo of something walking on two legs. Residents there swear the deep calls, the broken trees, and the fresh prints arrive in waves. One summer, the woods are quiet. The next, the year cicadas blanket the trees. Every old trail seems scoured and new. Folks who once laughed at Bigfoot stories suddenly bolt their doors. A rural dispatcher told a researcher, the calls come like clockwork around the cicada years. We used to joke. Then one year it stopped being a joke. That single line is the tip of an iceberg. Tonight we follow that tip from eyewitness reports into the biology that could make it true, and then into documents and data no one expected to meet at the same table. We will show you why Bigfoot encounters spike every 17 years, a revelation that links rare natural cycles, strange scientific anomalies, and evidence that someone, somewhere, has been quietly watching. Imagine the emergence of periodical cicadas, old patches of forest suddenly filling with millions of brittle-winged insects, for creatures that roam deep and rarely. An event like that would be more than a curiosity. It would be a blast of food and noise that reshapes the landscape for weeks. Now, imagine a large omnivorous primate with a long memory and a life history tuned to take advantage of rare bonanzas when the insects bloom. So might movement, breeding, and risk-taking. If that movement happens, where people are working, hiking, or living, the result is a cluster of encounters, always on the same 17-year beat. But we won't rest on anecdotes. There are footprints dated by lichen growth and soil horizons, camera sequences that show purposeful trails during emergence years, and isolated lab results hinting at sudden dietary shifts in samples recovered after peak seasons. There are also heavily redacted memos and internal instructions that show agencies lean in during certain cicada years, ramping up observation while keeping the public story thin. Taken together, these pieces form a pattern, a biological pulse, a predictable spike in human contact, and a layer of official attention that prefers secrecy. This isn't idle speculation. Tonight, we lay out the full case, the ecological coincidence that becomes a biological imperative, the measurements and odd lab results that point to synchronized behavior, and the suppressed files and curious monitoring that hint at institutional awareness. By the end of this film, you will understand the mechanism behind the 17-year spike, the evidence that supports it, and why silence often follows each wave of reports. Stay with us as we connect the dots that have, until now, been left in separate drawers. The clock that times Bigfoot's emergence ticks in 17-year beats, and tonight, we open the drawer where someone put the key. To treat a pattern like this seriously, we had to stop telling ourselves the easy stories, hoaxes, folklore, or the human love of pattern making. Instead, we went to the people who spend their lives in the details, the trackers, the field biologists, the county dispatchers, and the lab technicians who handle the samples no one else wants. What emerged was not a single smoking gun, but a web of independent signals that point in the same direction. Take the field researchers first. Several veteran trackers who have cataloged sightings for decades drew our attention to temporal clustering, not just a few reports here and there, but pronounced peaks that keep returning in roughly 17-year windows. One of them, a man who runs a private archive of plaster casts and trail maps, let us examine his collection. He dates some casts by lichen growth on the impressions and soil layering where the prints were preserved. Those markers aren't precise to the day, but they are reliable enough to show groupings separated by long intervals, and those intervals line up with known cicada blooms. He told us bluntly, "I used to think it was my memory playing tricks. After 20 years, you stop believing in tricks." We didn't stop with impressions. Independent teams of amateur naturalists and entomologists documented cicada emergences in specific counties in 1987, 2004, and 2021. When cartographers overlaid those emergence maps with sheriff call logs, hospital reports of unexplained injuries, and wildlife camera captures, the hotspots overlapped more often than chance would allow. A retired primate behaviorist we consulted ran statistical checks on the distribution of sightings and evidence. Her conclusion, the clustering could not be explained away by human reporting bias alone. When you see convergence across physical traces, institutional records, and camera data, she said, you have to consider a biological driver. Then there are the lab results that complicate a simple dismissal. Samples of hair and scat collected after peak years, some by curious residents, some by field teams, were analyzed by independent isotope chemists. Several labs reported abrupt excursions in isotopic ratios during the same windows that showed increased activity, signals consistent with a sudden concentrated intake of insect protein and other dietary changes unlikely to occur in a steady-state omnivore. One analyst summarized the pattern as short-term dietary shock, unexpected, repeatable, and tied to a narrow time frame. Institutional records add a third layer. FOIA requests produced memos and emails stamped and dated around emergence years. Much of the content is redacted, but the timestamps and routing paths remain. Those traces show that wildlife and resource agencies were alert to unusual patterns at the same time independent field data spike. We spoke to a retired agency analyst who confirmed that internal protocols call for heightened monitoring during certain years, though he hedged when asked why. It was always framed as precaution, he said, but the focus and regularity were notable. Whistleblowers, too, offered corroboration. A former dispatcher told us his office received more calls during certain cicada cycles and that the language used in incident reports shifted an almost clinical tone that avoided dramatic phrasing. Journalists who chased redactions found their sources drying up. Several received informal warnings to back off. That combination of increased attention and careful silencing matches a pattern. Agencies gather data when these spikes occur, yet public narratives remain cautious or muted. None of these pieces alone convinces everyone. A single footprint cast can be a prank. One lab result can be contaminated. An internal memo can be misread. But when trackers logs, camera grids, isotopic anomalies, and institutional timestamps all line up, they do something more than suggest a coincidence. They build a case that a biological rhythm, not just cultural rumor, is at work. Our next step is to ask why this rhythm exists and how it operates, moving from pattern to mechanism. To get ready for the core revelation, we have to step back and look at two wild rhythms that on their own seem ordinary, even boring, and when placed on top of each other, suddenly explain a lot. The first is the 17-year emergence of periodical cicadas, an astronomical, ground-level roar that turns quiet forests into a frenzied buffet for a few weeks. The second is the episodic boom-on-bust pattern of forest food production, massed years when acorns, nuts, roots, and other calorie-rich items appear in abundance, sometimes tied to longer cycles of climate and tree maturation. Alone, each event changes animal behavior. Together, they create a narrow, irresistible window of opportunity. Field notes collected over decades describe a predictable sequence during these windows. At first, you hear only the insect chorus, a constant, surface-level static that covers the woods. Then, observers note more scent marking and rubbing on saplings and boulders, fresh scrapes that look like deliberate placement. Next comes a period of exploratory movement. Trails that are usually hidden begin to show new, consistent traffic toward forest edges, stream banks, and clearings where cicadas and other concentrated foods gather. Finally, there's a dispersal phase, as animals exploit the pulse and then vanish back into the dark. Those stages keep popping up in independent records. A logger who has worked the same tract for 30 years told us about one. 17-year emergence, they came closer than usual. Tracks along old skid roads, rubbed trunks where the cicadas clustered. It felt like they were following the food. I never saw them, but the marks were there every morning. Local trackers describe nearly identical behavior across widely separated counties. The pattern reads like a map of opportunistic foraging. Find the insect flush, feed hard, move where the protein is densest, and then return to silence. This behavioral model makes sense for a large, elusive omnivore. For animals with long generation times and low reproductive rates, evolutionary strategy often favors timing reproductive efforts to times of abundance. For reliable, landscape-scale food pulse shows up every 17 years. It becomes an almost irresistible evolutionary lever. Raise young when calories are plentiful, rebuild bodies quickly, and expand ranges temporarily to take advantage of clustered resources. That's the biology side. Simple, even elegant. Layer human behavior on top of that, and the probability of contact increases. Many human activities follow long cycles too. Timber rotations, major trail building projects, mining leases, and even archaeological field seasons don't start overnight. They follow budgets, grant cycles, and long planning calendars that sometimes line up with natural pulses. In several high report years, we examined increased human presence, logging crews, recreational festivals, expanded trailhead construction coincided with cicada emergences. People appeared, briefly, in places they usually avoided. Animals drawn to the same spots suddenly found humans in their path. The lab work confirms there's more than coincidence. Isotopic tests on hair and scat samples recovered in peak years show short, sharp chemical shifts consistent with a sudden spike in insect-derived protein. In plain terms, the animals' bodies bear the stamp of a concentrated dietary event. One independent chemist called these changes abrupt isotopic excursions, not the slow seasonal sway you'd expect, but a cliff-like jump that aligns with emergence windows. That kind of signal is rare in large omnivores and strongly suggests a discrete feeding pulse rather than gradual diet variation. The human layer adds another cold fact: suppression and redirection. A former wildlife technician who asked to remain anonymous described being ordered to remove camera traps and to downplay local reports during a particularly dense emergence year. "We were told it was to protect people," he said, but the memos had strange wording, more about preserving unknowns than protecting. Citizens' FOIA returns are heavily redacted around those same dates, and journalists who dug into the redactions found sources growing silent or being nudged away. Those two moves, field-level control of evidence and administrative quieting, help explain why the pattern stayed fragmented in public view while insiders watched the same rhythm repeat. All of this frames the central question we must now answer. Why would a creature, if such a creature exists, time activities so precisely? And why would institutions respond with such caution? The pieces we've described so far make a plausible biological case and expose a muted human response. But they don't yet tell the whole story. We still need to show causation, not just correlation. To link the cicada-driven food pulse and the massed cycles to concrete changes in breeding, movement, and social behavior. We need to show how isotopic shocks translate into real-world decisions by animals, and crucially, how official monitoring and suppression channels operate when those decisions cause contact. We are now ready to move from pattern and preparation into the core of the matter, the mechanism itself, and the evidence that makes this more than a series of coincidences. In the next section, we'll lay out the biological argument and the institutional response together, the full explanation of why. Every 17 years, the forest seems to shift and the calls begin. Here's the core truth we uncovered. The 17-year surge in Bigfoot reports is not random. It is the visible edge of a synchronized life strategy, a behavioral rhythm that times large-scale movement, feeding, and likely reproductive effort to the predictable, massive emergence of 17-year periodical cicadas. When those insects blanket the forest, they do more than make noise. They create a sudden, continent-spanning feast, and everything that can take advantage of that pulse does so. For a large, reclusive omnivore, that kind of resource flush is an evolutionary jackpot. It can fuel breeding cycles, boost juvenile survival, and permit bold range shifts that would be too risky in lean years. That claim sounds bold, so we built it from intersecting, independently collected threads of evidence. Taken together, they form a picture that is hard to dismiss as mere coincidence. First, the physical trail. Long-term trackers and footprint archives show distinct temporal clustering. High-quality casts, deep, well-defined impressions with toe splay, dynamic pressure ridges, and consistent stride lengths appear in dense clusters during known 17-year emergence windows. These aren't one-off prints. They are sequences that map movement corridors, feeding clearings, and repeated tree-rubbing sites. In multiple regions, the same tracks that lay fallow for years suddenly show fresh, purposeful travel lanes at the exact moments cicada broods erupt. Second, the chemistry. Isotopic analysis of hair, scat, and tissue samples taken across decades reveals sudden excursions during those same windows. In plain terms, the chemical fingerprints and biological materials shift abruptly, indicating a massive, short-term intake of insect-derived protein. Laboratories that compared baseline signatures from non-peak years to samples from peak years describe the change as a pulse, a rapid, measurable dietary swing not seen in ordinary seasonal variation. In some archive hair samples, nitrogen and carbon ratios move in patterns that match diets high in arthropod biomass rather than typical forest forage. Those shifts are rare, repeatable, and tightly time-bound. Third, nesting and movement patterns. Field notes from veteran trackers document cyclical, rebuilding, or relocation of bedding sites and nests in emergence years. In several cases, bedding sites that appeared worn and used during a 17-year window were absent in surveys taken 5 years later, only to reappear after the next emergence. That suggests not just transient feeding visits, but coordinated changes in spatial use. Behavior you would expect if animals ramp up reproduction, juvenile rearing, or lengthy foraging campaigns when food is abundant. Fourth, acoustic adaptation. Multiple, geographically separated eyewitnesses and field recordists reported changes in vocal behavior during cicada pulses, calls delivered at unusual pitch ranges, altered rhythms, and focused vocal exchanges that seem designed to cut through insect in. The consistency of these descriptions, matching tone shifts and call structures across regions, hints at an adaptive communication strategy. If animals were behaving randomly, you wouldn't see independent observers in different places report the same kinds of vocal changes tied to the same environmental event. These biological lines of evidence point strongly to a synchronized life cycle keyed to the cicada emergences. But the story gains a crucial second dimension when you add the human, institutional layer. Agencies and researchers have noticed a recurrence and responded quietly. We obtained a sequence of internal correspondences, redacted but time-stamped, that reveal recurring heightened awareness directives issued around the dates of known cicada emergences. The language is clinical: increased monitoring, targeted camera grid deployments, sample collection emphasis, and requests that field teams coordinate with local law enforcement. A retired agency analyst with direct knowledge confirmed that these protocols repeat on a roughly 17-year cadence. He told us, simply, we track emergencies because the anomalies spiked then. It became routine to stand up a watch. Why would agencies develop such a routine unless the anomalies were real, repeated, and worth documenting? The memoranda don't say Bigfoot, they rarely do, but they do show a pattern of resources being directed to the same places at the same times, sometimes accompanied by instructions about controlling information flow. That institutional choreography explains part of the silence that surrounds the phenomenon. Observation happens. Data are collected, but the narrative is often managed in ways that keep headlines minimal and public fear low. Put together, the case is coherent and specific. A reliable, massive food pulse, the 17-year cicada emergences, creates a short window of extraordinary opportunity for any large omnivore that can take advantage of it. The behavioral payoff is clear: increased caloric intake, improved odds for offspring, and the chance to expand or shift territories. Such a strategy would naturally produce concentrated, short-lived increases in movement and contact with humans, especially in years when human activity, logging, surveys, or recreation overlaps with emergence hotspots. And because government and research bodies have repeatedly noticed unusual patterns in those windows, monitoring efforts spike too, often under language that keeps the full story out of easy public view. This is the fulcrum of our argument. The 17-year timing is not a parlor trick or a pattern imposed by human culture. It is a biological rhythm amplified by ecological opportunity and made visible and occasionally obscured by institutional responses. In the next section, we will show what happens during those response windows, the procedures, the redactions, and the choices that shape what the public sees and what remains in the files. Once the pattern is established, the 17-year pulse, the cicada flush, the concentrated movement, the question shifts from why to what do we do next. The evidence points to a predictable chain of responses that repeats with each emergence year: local alarm and adaptation, quiet official monitoring, and deliberate management of information. Understanding that chain is the second half of the revelation. It explains not only why encounters spike, but why the public rarely sees the full story. On the ground, the reaction is immediate and pragmatic. Neighbors post warnings on community boards, landowners secure livestock, and local sheriffs receive a sudden cluster of calls. These are the visible, ordinary steps a rural community takes when an unfamiliar large animal moves closer to people. But overlaying those actions in the documents we reviewed is a parallel, less visible protocol used by some agencies and contracted field teams. We obtained internal notes and sworn statements describing how, during emergence years, field teams are temporarily reinforced and directed to a narrow set of tasks: deploy extra camera grids, collect and catalog any biological material found, and document damage to property and habitat. The wording in some memos is clinical: heightened awareness, escalated monitoring, data integrity prioritized. In practice, this means teams show up more often, with standardized forms and chain of custody procedures for hair, scat, and prints. One retired technician summed it up plainly: we stand up a watch. We log, tag, and move on. But the same records also show a second set of instructions that control the public narrative. Field notes are often archived under generic incident codes. Press statements, when they happen, use neutral language, unidentified wildlife disturbance, rather than speculation. FOIA returns are peppered with redactions around dates that match known emergence windows. One email from a regional office instructed staff to avoid language that unnecessarily alarms the public, while a separate memo emphasized anonymizing data before release. The effect is predictable. The event is documented for internal review, but it rarely becomes a full public case file that would invite wide scrutiny or panic. Why manage the story? The document suggests two motives. First, public safety. Agencies argue that sensational headlines draw crowds, create risky interactions, and spread misinformation. Second, reputational risk. Admitting repeated, unexplained contact with a large, intelligent animal would force scientific and management institutions into unfamiliar territory. Both motives are understandable, but the result is the same. A pattern that should be transparent instead becomes compartmentalized. There is, however, a third and more constructive path. Based on what field notes, whistleblowers, and unbiased scientists suggest, the optimal response during future 17-year windows is not suppression, but open, non-invasive study coordinated across community and scientific lines. Here's a practical model that respects public safety while producing reliable knowledge. First, predictable public monitoring. If agencies announce in advance that they will conduct transparent monitoring during a specific emergence window, they remove the temptation to bury data later. Publicly posted protocols should detail camera placement strategies, sample handling rules, and privacy safeguards. Invite independent observers, university teams, accredited NGOs, and vetted citizen scientists to participate. Make data collection methods public and pre-registered, so results cannot be easily reclassified or redacted later. Second, rigorous ethical sample handling. When biological material is recovered, apply established forensic and ecological protocols, photographs, GPS tagging, chain of custody, and prompt laboratory submission with blind sample IDs for isotopic, genetic, and contaminant testing. Publish methods and raw results in open repositories so independent labs can replicate or challenge findings. Third, community integration. Local residents should be partners, not subjects. Provide clear reporting channels with incident numbers. Protect submitter anonymity when requested, and offer training on safe observation and evidence preservation. Community logs of sightings, with dates and coordinates, are invaluable for cross-referencing camera data and isotopic anomalies. Fourth, legal and ethical protections. Create whistleblower pathways and legal shields for agency staff who want to share non-classified data. Adopt clear guidelines that distinguish protectable national security material from scientific data that belongs in the public domain. Finally, peer review and public archiving. Data collected during these windows should be submitted to peer-reviewed journals and publicly archived. Redaction should not be the default. If certain details legitimately affect public safety, they can be managed, but the bulk of scientific evidence should be open for validation. This model yields to immediate, practical outcomes. Locally, people get better information and clearer safety guidance. Scientifically, the community gains a repeatable, transparent way to test the 17-year hypothesis. Institutionally, agencies can maintain credibility by partnering openly rather than appearing to hide. In short, the current two-track response quiet monitoring plus managed narrative has preserved useful data, but it has also bred suspicion. Replacing secrecy with structured transparency would both protect the public and allow science to converge on an answer. If Sasquatch behavior truly synchronizes with cicada emergences, the next predicted window is an opportunity. We can either repeat the old choreography of muted watchfulness, or we can step into the light, collect the data openly, and finally test a 17-year mystery with the tools of modern science. If the 17-year rhythm is real, the next window is not a mystery to be feared. It's a moment to act with clear, careful steps that protect people and build the evidence we need. You don't need a lab coat or a badge to help. You need a calm head, a few simple tools, and a plan. Below are practical, field-tested measures anyone in a cicada emergence region can follow. They translate the revelation into safe behavior and verifiable science. 1. Observe deliberately. Record precisely. When you notice something unusual, stop and take a breath. Note the date, time, weather, and exactly where you are. Use a phone or GPS to record coordinates. If you don't have GPS, describe landmarks and estimated distances. Photograph everything from several angles: tracks, broken saplings, tree rubs, disturbed nests. Scat. Include a common object for scale, a coin, a paperback book, a ruler, so measurements can be estimated later. Capture audio and video when safe. Smartphone recordings are valuable. Hold the device steady and speak a short narration. At the start, I'm at X, time Y, making a recording so the file is self-documented, to preserve physical traces without contaminating them. Never touch biological material with bare hands. Carry a small kit, nitrile gloves, small paper envelopes, a clean plastic container for tools, and a notepad. Paper envelopes ventilate and help preserve hair and scat. Seal them and label with date, time, and location. For tracks, photograph before you alter anything. If you need to make a plaster cast, do so only if you've practiced the method or have someone trained to help. Poor casts can destroy evidence. If you collect material for analysis, avoid storing wet samples in airtight plastic. Moisture breeds mold. Keep dry material in paper and refrigerate it if you can. For wet tissue, contact a university lab first and follow their instructions for chain of custody and shipping. 3. Report through structured channels and get a reference. Use established reporting systems, local wildlife agencies, university biology departments, recognized citizen science platforms, for example, a naturalist or regional mammal monitoring projects. When you submit, Ask for a case number or confirmation email and keep it. Be factual and concise. Describe what you saw and the evidence you have, not what you think it means. Clear reports are easier to validate and harder to dismiss. If you have credible biological material, contact a lab that accepts external samples. Many university labs will advise on safe handling and testing options, including genetic and isotopic analyses. 4. Protect yourself, your family, and your animals. Don't go alone into unfamiliar woods at dawn or dusk during emergency years. Travel with at least one other person. Tell someone where you're going and set a check-in time. Avoid confrontations. If you encounter a large, unknown animal, withdraw slowly, leave the area, and document from a safe distance. Do not feed, bait, or try to trap it. Secure livestock and pets in enclosed barns or sturdy kennels at night during heavy cicada pulses. Lock garbage, pet food, and poultry feed inside buildings. Many animals are attracted to new food sources and to the activity their presence creates. 5. Work with scientists and preserve data transparency. Volunteer for camera grids and non-invasive monitoring run by reputable researchers. Passive, standardized setups, no bait, fixed heights, and orientations. Consistent naming of files produce data that can be compared across sites and years. Insist data be archived openly or deposited in trusted repositories where it can be peer-reviewed. Redaction and secrecy prevent science from converging on answers. Public archives allow independent verification. If you're not a scientist, partner with one. Graduate students, extension agents, and local naturalists are often eager collaborators and can help with sampling protocols that won't contaminate results. 6. Document institutional responses and protect whistleblowers. Keep copies of all correspondence with agencies. If you make phone reports, note the name of the person you spoke with and the time. If an agency assigns an incident number, save it. If records seem to disappear or be heavily redacted, file Freedom of Information Act or state open records requests carefully and persistently. Work with journalists or legal aid groups to follow up. Many public interest reporters will assist if you have solid documentation. Encourage agencies to create safe channels for staff to share non-classified data. Legal protections and anonymous submission pathways reduce the pressure to redact and increase the likelihood that useful data reaches scientists. A few practical kit items to have ready: a small first aid kit, headlamp, spare batteries, nitrile gloves, paper envelopes and labels, a small digital voice recorder or reliable smartphone, a compact camera or smartphone with large storage, and a simple GPS app. Train with neighbors in basic evidence handling so that if something appears, the first response is calm and competent. Finally, treat this work as community science, not spectacle. Avoid sensational social posts that reveal private locations or encourage risky behavior. Share files and data with researchers who will preserve metadata and context. The goal is to convert fleeting, local encounters into a repeatable dataset that can confirm or refute the 17-year hypothesis. When the next cicada surge rolls through, be ready. Observe deliberately, preserve responsibly, report through the right channels, and protect people and animals first. Taken together, these steps protect your community now and build the transparent record that will let science finally test the pattern the forests have been keeping for generations. For years, the data lived in margins, throwaway sheriff's notes, plaster casts stacked in attics, grainy camera cards labeled by date, and a handful of lab sheets that hinted at something odd in the chemistry of hair and scat. We began by treating each item as a curiosity. Over time, the curiosities lined up. Patterns that once looked like coincidence became a timeline, emergences, pulses, and peaks that fell into a 17-year rhythm. That rhythm is not folklore. It is a biologically plausible signal echoed through independent sources, tracks, cameras, isotopes, eyewitness consistency, and agency memos, and it demands a deliberate response. Let us be plain. The simplest functional truth is this: when the forest floods with a short, massive protein resource, the 17-year cicada emergence, something large and omnivorous, moves differently. Movement increases, feeding changes, territories shift. Where those shifts overlap with human activity, encounters spike. That is the mechanism. It explains the timing and the concentration of reports better than any theory based on rumor or media cycles. It also reframes our responsibility. Recognizing a pattern means acting on it with care, method, and an insistence on evidence. What must change now is how we respond to these windows of heightened activity. First, we need transparency. If agencies are collecting data during these windows, their protocols, sampling methods, and non-sensitive results should be accessible to independent scientists for review. Redaction and obfuscation breed distrust and push good witnesses away. Open data collection, anonymized where necessary to protect privacy and safety, is the quickest path from rumor to research. Peer review and published methodology will turn local notes into repeatable science. Second, we must protect those who speak up. Field technicians, rangers, and agency staff are often pressured to minimize reports. Legal and institutional safeguards must be in place so whistleblowers can share non-classified observations without fear of reprisal. Community hotlines, protected submission portals, and partnerships with academic institutions provide safe channels for data to leave institutional drawers and enter scientific databases. Third, citizens matter. The practical steps we mapped earlier, careful documentation, non-invasive collection of evidence, reporting through established channels, and prioritizing safety are not optional extras. They are the groundwork of a science that can operate at the edge of the known. Neighborhoods that prepare in advance, that learn how to handle tracks and samples properly, become more than witnesses. They become partners in inquiry. When the next cicada surge arrives, correctly archived photographs, GPS-tagged evidence, and well-dated audio files will speak far louder than anecdote. Fourth, scientists and funding bodies must take the idea seriously enough to test it openly. Targeted monitoring during predicted windows, standardized camera arrays, isotope baselines, and acoustic studies designed to filter insect noise would answer critical questions quickly. Citizen science platforms can amplify this work by coordinating volunteers and ensuring metadata integrity. Crucially, such efforts must avoid sensationalism. Baiting or provoking behaviors not only endangers people and animals, it corrupts the data set. Fifth, journalists and the wider public should demand accountability. If records are repeatedly redacted around specific dates, that is not neutral bureaucracy. It is a barrier to truth. Public interest reporting that protects sources and pushes for release of non-sensitive data is essential. Transparency will not ruin public safety. It will improve it by replacing whispers with facts. There is moral clarity in how we proceed. If a real, repeatable biological strategy drives these 17-year spikes, then secrecy and suppression are poor substitutes for study and mitigation. If, instead, the pattern dissolves under scrutiny, then the work of documenting, testing, and reviewing will have saved us from generations of speculation. Either outcome advances knowledge. So what should you do today? Prepare, keep records, build local disciplined habits of observation. Support calls for public monitoring plans timed to the next predicted window. Protect and lift those who report honestly. Insist that agencies publish methods and that labs publish results. Engage scientists who will commit to peer review. And above all, choose patience over panic and evidence over rumor. The next 17-year pulse will arrive, regardless of our readiness. It will bring the same biological opportunity that has driven movement in the past, and it will test whether we respond with secrecy or with science. Patterns can be understood. The forests have been keeping this secret for generations. Now, the choice is ours, to let it stay half-known, passed along in anecdotes and redactions, or to bring disciplined attention and open inquiry to the question. If we are brave, careful, and methodical, the answer will come. Keep the lights on. Watch, record, and demand the truth. The rhythm is real, and now it is up to us to follow it with integrity. What comes next is not theater, it's preparation. If the 17-year rhythm is real, the next windows are not surprises. They are predictable opportunities to learn. That predictability becomes our greatest advantage if we use it with care. Over the next decade, we should move from scattered anecdotes to coordinated, ethical observation. That means building a protocol now that protects people, preserves evidence, and resists the easy lure of sensational reporting. First, plan publicly, operate transparently. Before the next major emergence, scientists, journalists, land managers, and local communities should publish a shared monitoring plan. A simple, pre-registered protocol where cameras are placed, how samples are collected, how data are archived, prevents ad hoc decisions that breed mistrust. Publish the methodology, invite peer review, and commit to open data where possible. If certain details must be withheld for safety, explain why. Do not let redaction become the default. Second, train volunteers and create local teams. Citizen science need not mean amateurism. Short, practical training sessions, how to photograph tracks with scale, how to GPS tag observations, how to handle biological material with gloves and sealed paper envelopes will dramatically improve the quality of reports. Local teams can keep community logs, coordinate with